Okay, so last time we started to discuss the idea about the inverse problems. And before that, actually, we also discussed some techniques about some conditional generation, either based on the fine tuning or without any kind of the training. And the inverse problem was kind of some the more the general case in terms of like basically how we can basically align the output of the hourly generation with the hourly observation, when there basically the relationship between the generated the output and the observation is basically defined in this way. So we are basically defining the relationship between the x and the y. So x is the hourly output, and also the y is basically the our observation as kind of some kind of the function. And typically this function is the linear function in many of the cases, right? So we have seen some multiple applications, including some like deep learning, like we are observing these blurry images and how we can basically reproduce the clean image, right? And also for the super resolution, that could be the case that we are having the low resolution image as the observation and generating the clean image, right? The high resolution image. And also for the in-painting case, we are assuming that we are having some kind of the partial input in terms of like having only the background and filling the mask region. So those are some of the applications of the inverse problems. So here, these are all the cases that we are having the y as kind of the given input. And then also typically, we are assuming here is that the a is not invertible. So if the a function is basically invertible, then we can directly compute the inverse of the y, just directly getting the x, right? But when you assume that the a is basically not invertible, so there would be basically the case that there can be multiple x that can basically match this kind of the output the y here. So in these kind of the cases, like how we can basically generate the kind of the data point x that can satisfy these constraints, right? So those are some of the cases that we are considering the inverse problems. And for them, basically what we discussed is that like diffusion model is like basically all about getting this core information. So if we can basically get the access to the information of the gradient, so the log of the probability, that basically is core information, right? So if we have this core information, then we can just like run the denoising process. So what we learned using the noise prediction network was this score, or the XT, unconditional score. And now what we want to do is that we are having the y as the condition. So given this condition, how we can get this score of this specific the probability distribution, right? Xt conditioned by y. So if we can basically compute the gradient of the log of this probability, then we can basically run the denoising process. And from the base rule, basically what we have seen is that actually to compute this, actually we just need this information, right? So if we have the DC information, y probability y conditioned by the xt, based on that we can compute the score of the xt conditioned by y. Why? Because like from the base rule, we could see that actually the score of like this term could be expressed as kind of the summation of the score of the xt, unconditional the score, and also the score of the y given the xt, right? So then it becomes that, so the final information that we need is actually this, xt conditioned by y. But now we can have this like unconditional score information from the noise prediction network. The only additional information that we need is just this information, right? So this is basically like what we need to compute. And using the CFG and also the classifier the guidance, we could see basically how we can compute that score, like y conditioned by the xt, by some kind of the extra neural network or fine-tuning the network, right? But here also the question is that how we can also achieve that information without extra detraining. It's basically training-free approach, right? So for that, basically, so what we could see is that while we do not know directly about the probability y conditioned by xt, we can basically get the probability y conditioned by x0. So this is kind of the given information, because like we modeled the inverse problem in this way. So this is basically our the known information about the relationship between the y and x0. So if we think about the special case, whether the relationship is basically some linear function, and based on the property of the Gaussian distribution, since the z is the sample from the unique Gaussian, from the property of the Gaussian distribution, we can actually see that this probability of the y conditioned by the x0 should be another the Gaussian distribution. So this is kind of like the already given information, the way that how we model the relationship between the y and the x0. And this relationship is determined based on each of the application, right? The given information. So if we go back to this, so we wanted to compute this probability of the xt conditioned by y. Then if we have this information about this curve like this, then we can run the denoising, right? We only know this curve for the xt, not this conditioned version. But what we can see is that if we know this part, score of the y conditioned by the xt, if we add this to the unconditional score, then that becomes score like this, the final score. So that's why we need to basically compute this probability y conditioned by xt. But this xt is the noisy data point, right? The things that we are denoising every time. There is no way that we can directly somehow like get the probability, this conditional the probability. But the only information that we can access is this probability of the y conditioned by x0. For the clean data point, basically we can get the probability of the y. Then what should be basically the way that we can connect these two? So we need some kind of the bridge connecting from the y conditioned by the x0 to the y conditioned by the xt. So to connect these two, now we are basically approximating another conditional distribution, which is about the probability x0 conditioned by the xt. So if we basically know this information from the base rule and also the marginalization, by combining the prior and the likelihood distributions, now we can compute this. Okay. So this is kind of the sequence of kind of the steps, like why we are basically requiring those information. Makes sense. So also what we have seen in the last time in the quiz is that if we also see that this both the likelihood and the prior distributions are also the Gaussian distribution, then the combination of like these two can be another the Gaussian distribution like this. So this is also kind of the known fact, right? So this is kind of things like we want to get this y condition xt conditioned by y. This can be computed by y conditioned by xt because when we know this for the xt, right? Want this, but we don't know exactly this. The only information that we know is basically this y conditioned by x0. So we want to basically get this information from this given information using some kind of a bridge, which is basically this information, x0 conditioned by the xt. But the thing is that also we don't know this. So it's basically a matter of like how we approximate this information. Okay? So, but the thing is that we still know the mean of that. The mean of the that conditional the probability x0 conditioned by the xt can be computed using the Twiggy's formula, right? So that's basically also what we have seen in the previous the lectures. So the only information that we know about this probability is that the mean of that the probability distribution, but we don't know the variance. Even we don't know whether this is normal distribution or not, right? So the only thing that we are doing is that we don't have the full information about that conditional probability. So let's basically just like approximate that with the given the mean information and also with some kind of the some arbitrary variance information. We just like set this variance to be basically like isotropic variance with the R squared. So this is basically our setup. Then now we approximate this information x0 conditioned by the xt. We know this information, right? By combining these two, now we can compute y conditioned by the xt. And if we add this to the score of the unconditional the score for the xt, now we can get the final this information. This is kind of the sequence of the kind of work that to compute the inverse problems. Makes sense? So after some kind of all the kind of calculation, what we could see is that this square, the extra term in the square function, y conditioned by the xt can be computed in that way with some kind of formulation, with some kind of difference here. and also the taking the gradient of the tweedies with respect to the xt. And this formulation actually became simpler when we set the R to be 0. So if we assume 0 variance, which means that given the xt, we already specifically sample the mean, the tweedies, the output as the x0. No variance. We already sample the mean, right? If we basically have this kind of very strongly assumption, now then even the gradient, the square function of the y in the xt becomes like this simple, right? Because taking the gradient of the L2, the loss, the difference between the y and the mapping of the tweedies here, and taking the gradient with respect to the xt. So you can see that actually, while we have seen some kind of some complicated formulations, actually all the computation is like quite simple. We just need to take the xt every time, taking tweedies, mapping to the y space, taking the L to know, and taking the gradient. So you see that actually this is really literally like the few lines of the code. It's very simple. And even the simpler thing is that this is like all about basically adding this as kind of the extra discord, right? So this is kind of some offset to our discord term, right? So which means that we are basically calculating the noise here, right? So instead of like using this noise, actually we need to add some kind of the extra the noise here, right? But adding that noise here actually becomes the same as kind of adding the extra noise here with some kind of the scaling term here. So what we can actually see is that this is basically nothing but running the typically denoising the process, either in the DDPM or DDIM framework, while basically adding one more line, which is about like taking the gradient descent with the L2 loss with respect to the xt term. So you see that this is really one line of the code in terms of adding some kind of guidance. Okay. So I just wanted to emphasize that, like, while we have seen some kind of formulations in terms of how we derived the final formulation, in terms of the implementation, this is like very simple, just like adding one line of the code. So in terms of like how we also control the scaling term. Makes sense? So actually, this is kind of the power of the diffusion models. So one of the really biggest power of the diffusion model is that for many kind of some conditional generating the setup, for example, like for the super resolution or like in painting, deep blurring, like those are like all different problems, right? But for all these kind of different cases, we don't need to train the diffusion models like all separately. We can just like use like one single diffusion model, like stable diffusion, and just do this kind of some guided generation with some kind of some guiding from here. Then we can actually handle multiple applications with a single diffusion model. So that's basically the big power of the diffusion models that we can see. It was not possible with the GAN and the VAE, but we are basically having this kind of property for the diffusion model because of that we are having the iterative process. So all the kind of denoting the process, we can basically add this kind of guidance in terms of that we are making the trajectory of the xt to be guided into some specific the desired output. So this is really kind of the powerful point of the diffusion models. Any questions on this? So as a kind of a quick remark, like basically so I'm going to show briefly is that actually this idea can be generalized into many other physics. So it doesn't need to be basically having that objective function as kind of the L2 loss between the observation and also the mapping of the tweedies. But actually it can be applied for any other things. For any tweedies, sorry, this should be tweedies, for any tweedies input, and also for any kind of the loss function or some objective function, the L there, we can basically put this kind of guidance. So we can generalize this idea practically for many other applications as well. Like one of the examples for that is basically like style similarity. So let's say this is kind of an example that we are basically converting this image into different style, like having this style, that style. Those are the styles. You can say that the whole structure of the image is preserved while basically matching the style of those images, right? So how can we do this kind of thing? Do you have any kind of imagination, like how we can do this? Any thoughts? So we just need to have some kind of the objective function that can basically measure the style similarity. So what we can typically do for these kind of tasks is that we first run the inversion of this image and rerunning the denoising process while basically adding some kind of the guidance. For the guidance, we just need to define some kind of the style similarity, which becomes a function in a way that we can run the backpropagation. So that's the only thing. You can see actually this is really simple. You just need to run the inversion that we discussed before, rerunning the denoising process while having some kind of the objective function for the style similarity. So it's only the matter of like how we define the some loss function for the style similarity. And there are lots of the options for that. One typical idea for the style similarity is that basically we are taking some kind of some neural net features for some kind of the pre-trained neural network, like VGG network or something else, like Dino or something. And basically measuring the kind of the output distance of some neural net features. So I mean, these are some very practical ideas. There's no guarantee, but this is like what people are really doing in terms of measuring some style similarity, like just like run some kind of the neural network with the input the images, extracting some kind of the intermediate features, and measuring some kind of the outputs. So you can check out the method called the LPIPs. This is like some very practical ideas about how we can measure the style similarity. But you can see that actually this is kind of very simple the idea. We just basically feed the images into the neural network, extract some kind of features, measure the distance there, running the backpropagation. So then you can achieve those kind of results. So you can see the procedure, right? Running the inversion, denoising again, while basically having the objective function of the style similarity. And this can be applied to the many other applications. What people are doing for the molecular structural degeneration is that we are also basically running the denoising process, while basically defining some kind of the constraint with some kind of the objective function. So it's like all the matter of like how we design this kind of some loss function to give some kind of the guidance. Then you just need to basically run the backpropagation at the every step of the denoising process. Makes sense? So one more example that we can also think about is that we also discussed this synchronization last time. Do you remember? That this is the assignment to find, right? So basically, we could see these kind of results by running the denoising process jointly from multiple frames, right? But one of the kind of the downside that we could see is that while basically this looks kind of like very seamless, smooth, and the panoramic images, now you can see that the style of the images are basically varying over the space. So here we are basically seeing like the nighttime image, and there we are seeing the daytime image. So it's not really about the making the image for the same scene. We are basically changing some kind of environment like over the space. So this is basically not really making realistic the panoramic images, right? So how can we make some kind of the more consistent outputs? So if we want to generate like this kind of more consistent the outputs, what should we do? And for that, basically, we can think about like combining synchronization with the kind of the guided degeneration. So the idea about the synchronization is basically, averaging something. So it can be xt there, or epsilon t, or the twins, right? So we discussed the multiple options for the synchronization. So let's think about the simplest case that we are taking the average of the xt minus 1. For that case, before we take the average of the xt minus 1, what we do is that we first take the twins here, run this style dissimilarity, measuring the style dissimilarity, and then running the backpropagation all the way to the xt. So updating the xt based on the loss function there, running the backpropagation. And then based on that updated the xt, now we sample the xt minus 1 and take the average. So this is basically the typical idea in terms of that we can also combine the idea of the synchronization with the guidance generation. then we can also produce this kind of some more consistent images as well. Makes sense. Yeah. So these are some kind of all the ideas that we discussed before in terms of like how we can utilize some kind of the pre-trained diffusion models for the multiple, some kind of the conditional generation applications. We discussed the control net for the classifier, the free guidance, and the DPS, and also the SDB. So can you guess like when we need to use like which technique? So if you have some kind of the chances to like apply some kind of those kind of ideas for some conditional degeneration, you might need to think about like which technique might be the best fit for each of the application. So can you see kind of some differences across those things? Any ideas? So you may use the control net for the cases that when you have some sufficient amount of some training data. So what we discussed with the control net is that it's basically fine-tuning the network. So while we are basically having the unconditional diffusion model trained with the billions of images, let's say like we still have some kind of the few like amount of images, like tens of thousands of the pairs. So it should be basically the pairs, like the input-output pairs, right? Like some sketch images and the realistic images, and the depth image and the realistic images, right? So when you have this kind of some pairs, to be like the sufficient amount of the pairs, like not just like 10 something, but more than like hundreds, thousands of things, then we can consider using the control net. So we basically, to use the control net, we should have some kind of the enough number of the training data, the way that we can fine-tune the network. That's the first condition, right? Without the training data, we cannot use the control net, right? And also the condition and the output should be same the modality. It should be both images, both video, both something. You see, is the point, right? So we saw some of the examples that we are taking sketch image as the input and generating some realistic images, or some kind of a pose image and realistic images, like having the same the modality for the input and the output, for the condition and the output, the image or something. And also one more thing is that the condition and the output should be spatially aligned, which means that like if we basically also like taking some kind of sketch of the bird, for example, we don't expect to generate some kind of the flower images, right? So pixel-wise, there should be some kind of some sort of the alignment. It may not be perfect alignment, but we are assuming that the condition and the outputs are basically having some sort of the pixel level of the alignment. Otherwise, it's hard to get some kind of good results with the control net. One of the kind of example that we are having the enough number of the training data and also the same modality, but not spatially aligned. I think we also discussed that application. Yes. One of the kind of the example for the cases that when the images are not aligned spatially was the Nobel synthesis. For example, like I have some kind of image from the front view, and based on that, I want to generate images of the side view of the same object. So for those kind of cases, like how should we tune the network? But in this case, like it's hard to expect that the images are like spatially aligned because like one is the view from the front image, and the other is the image from the other view. Then these two will not be spatially aligned, pixel level aligned, right? For those kind of cases, we cannot expect that the control net would work. For those kind of cases that we are having some kind of enough number of the pairs of the condition and the output for the fine tuning, but if the input and the outputs are not spatially aligned, or if they are even not having the same modality, then we can consider using the classified free guidance or classified guidance, depending on like what's the condition. If the conditions are the classes, then we can really consider using the classified guidance. But for many of the cases, we can consider using classifier free guidance. So for any kind of the condition, so it doesn't need to be same modality. It can be text to image, or like label to image, or even image to image when they are not spatially aligned. For many other cases, we can think about like using the classified free guidance. We can really think about like fine-tuning unconditional model by adding the extra condition. while basically changing the loss function is kind of the modified the noise with the classified free guidance. Make sense?
You said fine-tuning is possible for classifier free guidance, but stable distribution, like those pre-trained model, do not accept the condition that I personally define. So how is it possible to fine-tune?
So the typical idea for the fine-tuning is that you are just like having another encoder for the extra the condition. So actually that was like 0, 1, 2, 3 is like one of the example, like for the Nobel synthesis. We are taking extra the image information as kind of the new condition, right? Then you need to have the extra the encoding network for that condition, the new condition, and feeding this information into some part of the neural net using some kind of the attention or something. So it's the middle of like how we design the neural network. But typically the idea for that is that you are just like making the encoder for the new condition, and then basically training this kind of whole network while basically having the new part, new branch of the network. And then changing the loss function. The loss function is the same, but we are changing the output noise as kind of the classified free guidance noise, the modified the noise. So that's the typical the idea. Actually, you can see that many of the conditional generation network generating images are either fine-tuned in the control net or CFG. For many kind of like some cases that we can use the control net, then control net is the best option. But when the input is not spatially aligned, or when the input is the different modality, then we can still try to use the classified free guidance. Makes sense? So those are some of the cases that when we have some kind of the data that we can use for the fine-tuning. So it's basically training-based or fine-tuning based approach. But if we do not have any kind of the data for the fine-tuning, then we can consider using the idea of like DPS, which is the solving the inverse problems without any kind of fine-tuning. So that's all becomes about like defining some kind of the objective function and running basically the backpropagation. So also the advantage of like this idea is that even we do not need to have the condition the output the pairs. The constraint can be defined with the some kind of the loss function, any kind of objective function. You don't need to basically somehow define the data for the condition. The condition can be just like formulated into some kind of objective function. Like for the style similarity, you can have some kind of a reference image where there can be some kind of the some style factor there, right? So many kind of the cases, we can just like define the constraint as some kind of objective function. Also, one of the example for this is that, for example, let's say I make some kind of the some human motion, human dancing motion, or human some kind of walking motion in the space. But I assume that there are some kind of the obstacles in the space. So I want to make some kind of the trajectory of the motions that can avoid all these kind of obstacles, right? So for those kind of cases, we can consider define some kind of the loss function that basically detects some kind of collision with the obstacles and basically give some kind of the values for that. Then we can, if we have some kind of penalty function for that, then we can run the backpropagation through the noise data point xt. So these are the cases like when we do not have some kind of the pairs, or when we cannot define some kind of constraint as kind of like data-driven way with some kind of condition the output pairs, but with some kind of objective function. But this is still the case that the function should be differentiable. If the function is not differentiable, that becomes some kind of the big problem. So then now we need to really think about like using the reinforcement learning, many other things. So that's kind of thing. So it's always better to have some kind of like differentiable the objective function. If this function is not differentiable, then you need to use some kind of the bigger tool, like some reinforcement learning, some many other things. So this is kind of the case. So SDAD was also kind of a special case that even the relationship between the condition and the outputs are not clearly defined, either in the data-driven way or in the, with some kind of objective function. So in the previous case, was basically defining the relationship between the condition and the output with some kind of the sufficient amount of the training data, that we are basically providing lots of the examples. Like you should have this output for this condition, data-driven way, just providing lots of the data, or defining the relationship as some kind of objective function. But in the SDAD, we also don't know. We don't know any kind of the relationship between these two. The only thing we know is that the condition is still having the same modality with the output, but the condition may be some kind of the slightly less realistic kind of the data point. And from that kind of the less realistic data point, we are finding some kind of the closest realistic data point. So it's more about some kind of the projection to basically realistic data point. So those are basically the four cases that we discussed. It's kind of some conditional generations. Can you say some kind of difference between these four cases? So I hope you can now see like what's the difference between, of course, like those four cases. This basically means that there are lots of the options in terms of how we can turn our basically unconditional model into some kind of for the conditional generation. But depending on the specific situation and the application, we can consider choosing all those things. And you can also even think about like combining some of those kind of things for the methods. Any questions on this? Any questions on the Zoom side? Does spatial averaging implies grand matrices? Spatial average, I don't know where we got the context of the spatial the average, but the grand matrix is also kind of one of the way to measure the style similarity. So for this style similarity, actually, there are multiple ways to basically define those forms. Any other questions?
The classifier free guidance, what if your label is not us? What if it's like floats? How do
you can use anything. I mean, for the text to image, sorry. Actually, even we are using the classifier free guidance for the even for the text input. It can be audio input. It can be many other things, even for the numbers. Yeah.
So for the classifier free guidance for the class, we sometimes like hide the actual class, like 0. You just give 0 to class.
Oh yeah, you need some kind of null class. Yeah. So it's also a matter of like how you define the null token. For the text to image, there is also some typical way to define some kind of null token. But for any kind of, there are also even some examples for the audio to image or audio to video generation. For those kind of cases, it's all a matter of like how you define the null tokens. And also kind of some small hidden thing in the classifier free guidance is that in the classifier free guidance, one of the kind of the main ideas is that we can use a single network both for the conditional and the unconditional denotes, right? By introducing that null token. But actually, we can consider just like making two different networks for the conditional and the unconditional case. It's just a matter of combining the two nodes. So, but I mean, yeah. So you can basically define the null tokens based on the kind of the input that you have. Any other questions? Okay. So this is kind of the sorry, the question in this Zoom chat. So when synchronizing epsilon within the canonical space, should we re-amplify the changed variance? So that's kind of the reason why it is not the good idea to synchronize the epsilon. But so that can be actually, that's one of the reasons like why it's better not to synchronize the epsilon, but synchronizing the TOIDs. Because for the TOIDs, we don't need to worry about changing the variance. Good question. Any other questions? Okay, so this is kind of the summary for the some guided generation or the conditional generation. And next week, we're gonna switch the gear into the slightly more theoretic things in terms of how we can also boost up the generation, the process, and then we can also move on to the flow-based model. So, no questions. Then before we